Now let me give you a general overview to what probability is all about. And as I've defined before, probability deals with the likelihood of an event occurring. So mathematically, the probability of an event A occurring is given as probability of A, P of A, is equals to number of favorable outcomes to A over total number of outcomes. So to get the probability of A, we first have to count the number of outcomes that are favorable to A, then we divide it by the total number of outcomes. This formula is really important and forms the backbone of most of the probability questions you are going to be tackling. So you have to do well to understand it and to know how to apply it. So now usually our probability values usually range from 0 to 1. When you have a probability of 0, it means that the event cannot happen. So as an example, think about the probability of having a man that is as tall as 10-story buildings. Now you know that based on the law of biology and nature, this is practically impossible. You cannot have a man as tall as 10-story buildings. So the probability of having a man that is this tall is equal to 0 because it simply cannot happen. How about 1? When you have a probability value of 1, it means that it will certainly happen. And think about it. What is the probability that night is going to fall today, or there will be nightfall today? It's definitely 1, because you know that every night there's usually nightfall. So the probability of nightfall occurring today is 1. How about the probability that we all eventually die one day or the other? Probability that we die one day of the one will die is 1, because it's a certainty. I know that everyone will eventually die. So this kind of probabilities in which you know will certainly happen are what? 1. While those that can never happen are what? 0. So normally, and most of the questions we'll be tackling are probability values that fall between 0 and 1. So when we have probability values that lie within this range, so when we are talking about the probability, for instance, that a man will live up to 50 years old. So a man will live up to 50 years old. Now we know that it's very possible, but there's a possibility that he might not live up to 50 years old. There's also a possibility that he might exceed 50 years old. So this kind of probability lies between 0 and 1, because we know that it can happen, but we are not certain that it will definitely happen. So they fall between 0 and 1, and that is most of the nature of the scenarios that we face in real life. So probability value from 0 to 1 is given in fractional terms, and also it can be represented as from 0% to 100%. Just make sure to note the unit and to convert to the fractional terms appropriately. So let's talk about theoretical probability. So this is the probability deduced through mathematics and reasoning. So when we are trying to deal with this kind of probability, what we are trying to do is we are trying to use our reasoning and our mathematical formula to try to figure out what probability is. So let me give an example of theoretical probability. Let's assume that a coin is tossed. What is the probability of a head showing up? So this coin shown here is the 25 kobo coin, and I'm sure most of you never saw it. I'm not even sure I did, but it was used, as you can see, the year was 1991, a really long time ago. So this was 25 kobo coin. So now let's imagine that you throw this coin. So now you know that there are two possibilities. The head can either appear, which is this place facing up, or the tail can appear. So the head can show up or the tail can show up. So there are two possibilities. So the total number of total outcome is how many? Is equals to 2, because you can either have a head showing up or the tail showing up. But now the question asks us to find the probability of the head showing up. So if there are two possible outcomes, how many of them is favorable to the head? So you see that the head can only occur maybe once, only one time. So as we know, the probability of having the head is equal to the number of outcomes favorable to the head, which are found to be 1, number of head occurring, which is 1, over the total number of outcomes that are possible. And the total number of outcomes that are possible is 2, because you can have either the head or the tail. So the probability of the head occurring is 1 over 2, which is the same as 0.5. So this is the basic idea behind the theoretical probability, which we are using our reason to solve. Let's take a look at another example. So now we're told that if two coins are tossed, what is the probability that number one, both coins will reveal the tail, and number two, one will reveal the head and the other tail. So now let me draw kind of like a table so that you can see the possible outcomes. So our first goal now is to find the total number of possible outcomes. So let me draw this, and this rule or this column here will represent the first coin. So for the first coin, you can either have a head or the tail showing up, while for the second coin, you can either have the head or the tail showing up. So here, what are you going to have? You can have your head, your tail. I'm going to explain this soon. Your head and your tail, and here you have your head, tail, head and tail. So what does this table mean? So now for this first coin, which is blue, and for this second one, which is red, you can see that when I throw the two coins together, there's a possibility that both of them will show up with the head. So that is what this result here represents, both of them showing up the head. There's also a possibility that the first coin will show up with a head, while the second coin will show up with tail. Now the third possibility is that the first coin will show up with the tail facing up, while the second coin will show up with the head facing up. And the final possibility is that both of them will show up with their tails both facing up. So as you can see, the total number of outcomes here are 1, 2, 3 and 4. So the total outcome is equals to 4. So the question asks us to find probability that both coins will reveal tail. So out of these possibilities, these 4 possibilities, how many of it has both of them revealing tail? We can see that this is the only option in which both of them are both tail. So the probability of having both of them as tail, probability of tail equals to how many times does it appear? It appears just once over what is the total number of possible outcome? 4. So you get 1 over 4, which is the same as 0.25. Yeah. So let's move on to the next question, or the B part, that says what is the probability that one will reveal head and the other will reveal tail. So we know that the total number of possible outcomes is also 4. But now what is the probability that one will reveal head and the other will reveal tail? We see that there are 2 cases in which this is possible. And this is the first case, when the first coin shows head and when the second coin shows tail. You have what? 1 head and 1 tail. Also, it's also possible if the first coin shows head, shows tail, and the second coin shows head. So here you see that you have what? 2 possible outcomes that are favorable to 1 head and 1 tail. So the probability of 1 head and 1 tail will be equal to what are the total numbers of outcomes that meet this condition. This outcome meets this condition and this outcome also meets this condition. So you have what? 2 over what is the total number of outcomes? 1, 2, 3, 4. We have 4, and 2 over 4 is 1 over 2, which is equals to 0.5. So now I should mention that this question can be set in a plethora of ways. For instance, you can be told that if 3 coins are being told. So in general, you should put at the back of your mind that to know the total number of outcomes when a coin is tossed. So in general, you should memorize this formula, or in general, total number of outcomes for coin is equals to what? 2 raised to power n. So as we solved in the previous example, when we were just tossing 1 coin, we had 2 possible outcomes. So 2 raised to power 1 is 2, and that includes the head and the tail. So if we are tossing 2 coins, we have 2 raised to power 2, that is 4 possible outcomes which are being shown here. So if you are tossing 3 coins, you have 2 raised to power 3, which is 8 possible outcomes. And your task now is to try to figure out what those 8 possible outcomes will be if you toss 3 coins. So now let's move on to a die. So if a die is rolled, what is the probability of a 1 showing up? So I'm sure that you all know what a die is, and this is the diagram of a die. So when you throw a die, you know that a die has 6 faces labeled from numbers 1 to 6. So the total number of outcomes is equals to how many? Is equals to 6. And why is that? Because the coin or the die rather can either show up with a 1 facing up, it can show up with a 2 or a 3 or a 4 or a 5 or a 6 showing up. So know that there are 6 possible faces that can show up. So the total number of outcomes are what? Is 6. So but the question asks us to find the probability of a 1 showing up. So out of that 6 possible outcomes, how many are just favorable to a 1 showing up? So if you look at our set, you can see that there is only one there. So the probability of a 1 showing up, or the number of ones that can appear, is just ones. So the probability of having a 1 showing up will be the numbers that are favorable to 1, which is 1, over the total number of outcomes, which is 6. So the probability of a 1 showing up is 1 over 6. So that is our answer. But as a side note, let's assume now that we are told to find the probability of a 3 showing up. So what will be the probability of a 3 showing up? So how many times does a 3 appear in this set? So the number of times a 3 appears is also 1, while the total number of possible outcomes is 6. So as you will see, the probability of any face showing up in a die is 1 over 6 when we are dealing in terms of theoretical values. So let's move on to another example, and here we are told that if 2 dice are rolled, what is the probability of both die showing a 6? So you have 2 dice now, and what is the probability that both of them you will have what? A 6 and a 6. And this game is really, having a 6 and a 6 is really important if you are familiar with the game of Ludo. So what is the probability of throwing 2 dice or rolling 2 dice and getting double 6? So now we start out. So we are going to represent this column vector here, or this volume face, with the first die. So this is die 1, and the one in this horizontal here as what? Die 2. So for die 1, you have 6 possible, you have 6 possible faces. So it can either show up with 1, 2, 3, 4, 5, 6. The same with die 2, it can either show up with 1, 2, 3, 4, 5, 6. So if it is showing up, so if you throw both of them together, they can both show up with 1, 1. And that is what this means. It means that the first or the second die can show 1, and the first die will show 1 also. This value here means that the second die can show 2, and the first die will show 1. This value here means the second die will show 3, and the first die will show 1. This value over here means that what? The second die will show a value of 3, while the first die will show a value of 4. And when you list out all the possibilities and you count out the number of outcomes, see that this is a 6 by 6, so you get what? 36. So if you count the number of possible outcomes, you see that it equals to 36. So the number of possible outcome is equals to what? Is equals to 36. But the question asks us for the probability that both of them will show 6. So now, out of all these possible outcomes, which of them has a result of showing just double 6? So you can see that showing of double 6 only occurs here, and it only appears only once. So number of having what? Double 6 is what? 1. So I can write out now that the probability of having 6, 6 will be equal to what? The numbers that are favorable to 6, 6, which in this case there's only one outcome that satisfies this condition, over the total number of possible outcomes. And as you can see, there are 36 possible outcomes. So when you throw your die, there's a 1 in 36% chance. So there's only 1 in 36 chance of getting a 6, 6. So now in general, you can be asked to find the probability, maybe if you are given 3 dice, 4 dice. So to know the total number of outcomes, total number of outcomes for multiple dice is equals to 6 raised by n. Remember, for our coin we had 2 raised by n. Now for our dice we have 6 raised by n. So when you are just throwing 1 die, the number of possible outcomes is just 6. When you are throwing 2 dice, as you see, it will be 6 raised by 2, which is what? 36. The number of possible outcomes will be 36. Now if you are throwing 3 dice, the number of possible outcomes will be 6 raised by 3. So let's move now to the idea of experimental probability. So from when we are talking about theoretical probability, what we did was that we tried to use our logic and reason to figure out what the probability will be. But in case of experimental probability, we don't need to do that. Here we carry out actual experiments, and based on the experiment you carry out, we can determine the probability. So here we determine the probability based on the number of trials that we've conducted. So we're actually carrying out experiments to determine the probability. And I'm going to give you similar examples so you can easily compare. So let's look at this example. A coin was tossed 10,000 times in an experiment. The result is summarized in the table below. Find the probability of a head showing up. So we know that the probability of an event A, just to recap, is equals to outcome of A, or outcome favorable to A, over total outcome. So now we have two possible outcomes, head and the tail, and they're asking us to find the probability of the head showing up. So we know that what the probability of the head showing up will be equals to what the number of times that the head appeared, and we can see that the number of times that the head appeared was what 4950, while the total outcome, and we can see that our experiment was carried out 10,000 times over 10,000, and that gives us what 0.4950. So now how about finding the probability of the tail? So in the same idea, the probability of the tail will just be equal to the number of times that the tail appeared, which is 5050, divided by the total number of times that the experiment was conducted, which is 10,000, and that gives us 0.5050. And as you can see, these values differ slightly from the theoretical value, which we got to be 0.5, but we'll talk about that briefly and shortly. So let's take a look at this example. So here we roll a die 200 times, and the outcomes are shown in the table below. Find the probability of obtaining a 1, 5, and 6. So now the total number of outcomes is 200 because we tossed the coin or the die 200 times. So, and based on the frequency now, we're told that 1 appeared 25 times, 2 showed up 30 times, 3 showed up 45 times, 4 showed up 28 times, 5 showed up 40 times, 6 showed up 32 times. So in the same idea, using the same logic, the probability of 1 showing up is equal to the number or the frequency of 1, which is thought to be 25, or which is given to be 25, divided by the total number of times the experiment was conducted, which is 200. And that is equals to what? 0.125. How about the probability of having a 5? So the probability of having a 5 just be equals to the number of times that 5 appeared, which is 40, divided by the total number of choose, which is 200, and that gives us what? 0.2. How about the probability of having a 6? The probability of having a 6 is just because the number of times that the 6 appeared, which is 32, divided by the total numbers of choose, which is 200. And what does that give us? That gives us what? 0.16. So now if you recall, when we were talking about theoretical, we got a probability of either getting 1 to be equals to what? 1 over 6 when we're talking about our theoretical. So now let's go to the comparison between our theoretical and experimental results. So now for the tossing of a coin, we see that our theoretical value for the probability of head, we got it to be 0.5, and the probability of tail, we got it to be 0.5. While for the experimental value, our probability of head was given to be 0.4950, and our probability of tail was given to be 0.5050. So as you can see, this value here is based on what we did in reality, and we can see that these values 0.5 is close to this and 0.5 is close to this. However, for the chain of the die, our probability of 1 and 5 are all the same when we're dealing with theoretical values, and which was equals to 1 over 6. But when we're dealing with it experimentally, like we performed it actually, our probability of getting 1 will go to be 0.125, and our probability of 2 will go to be 0.2. You can see that this value is slightly different, and these values also are slightly different from one another. So that is what happens when you are dealing with experimental probability. So as you try, or as the number of time increases to infinity, or as you perform your experiment to a very large number of times, then it gets close to the theoretical value. As you can see here, since we toast it 10,000 times, you can see that our values were quite close here. So let's say we're able to throw this die for 10,000 times, you can begin to get results that are closer. But this just give you the idea, basic idea behind theoretical values and experimental probability. So the sums of probability, so normally the sums of probability must be equals to 1. So if you have three events A, B, C that are mutually exclusive, and I will explain what mutually exclusive later. So if you have three events that are mutually exclusive, then the probability of A plus the probability of B plus the probability of C must be equals to 1. So put it at the back of your mind that when you sum up all the possibilities, they must add up to 1. If it exceeds 1, then you should know that you've made a mistake somewhere, and if it's greater than 1, note that you have made a mistake also. So let's move on to the idea of complement. So if the probability of A plus the probability of B plus the probability of C is equals to 1, then the probability of not A, which is defined also as the complement of A, is equals to 1 minus the probability of A. So, and 1 minus the probability of A, if I make the probability of A the subset of formula, I can see that the probability of A is equals to 1 minus the probability of B plus the probability of C. So what does that become? That becomes 1 minus, when I substitute this, I have what into bracket 1 minus the probability of B plus the probability of C. And what does that give me? That give me 1 minus 1, then plus probability of B plus the probability of C. And that is why this cancels this and I left with this. So the complement of A, just put at the back of your mind that the complement of A can also be given as probability of the complement of A, with this symbol over here as we discussed in set, is equals to 1 minus the probability of A. The same logic applies. The probability of B complement or not B is same as 1 minus the probability of B. And finally, the probability of C complement is equals to 1 minus the probability of C. So the idea of complement is really important in some questions, as it can save you the time that it gets to tackle a certain probability question, as we shall see very soon. So that will be all for now. So let's move on to the next section.